All right, so today we'll be talking about momentum, week one. Next week, we'll continue more with collisions in 2 dimensions. First of all, what is momentum? Momentum is basically an object with mass in motion. It's represented by the letter P, and it has the formula P equals mv, where m is mass and v is velocity. Since m has units of kilograms and v has units of meters per second, we know that momentum has units of kilograms times meters per second. Kilograms times meters per second is also equal to newtons times seconds. And since newtons is the unit of force and seconds is the unit of time, we know that newtons times seconds is equal to force times time, which is also equal to momentum. And this can also be proven when we think about F equals ma, where a is equal to the change in velocity over time. So therefore, force is equal to mass times the change in velocity over time. So if we assume that the mass doesn't change over time, we also have that force is equal to the change in mass times velocity over time, and therefore force is equal to the change in momentum over time. So basically from this slide, we can take away that force is equal to the change in momentum over time, momentum is equal to mass times velocity, and its units are kilograms times meters per second. Let's start off with an example. A car is moving with a velocity of 29 meters per second, and it has a mass of 1.3 times 10 to the third kilograms. So what is this momentum? I'll give 3 seconds to pause, and then we'll go over the answer. This is a really straightforward problem. It's simply that momentum is equal to mass times velocity. And when you multiply the two given quantities, you should get 3.8 times 10 to the 4 kilograms times meters per second. Momentum is also conserved, so it's one of our conserved quantities along with energy in the AP Physics syllabus. So the initial momentum is equal to the final momentum, which basically says that momentum initial is equal to momentum final, and therefore the mass times the initial velocity is equal to the mass times the final velocity. But this is only true when the particles have no electric charge and they're isolated. So they're in an isolated system with no external forces. So this concept is really simple, that the momentum before equals the momentum after, but when combined with energy, it can be really helpful in solving problems that appear to use kinematics, and it can also be more elegant. And this is especially true when you're dealing with heights and curved surfaces, because kinematics may be very tedious in those examples.
So now we're going to be talking about impulse and momentum. And impulse is really just the change in momentum, and it is used with the variable j, or sometimes I as well. And it is, as this formula says, the change in p, which is momentum. And a lot of times this is expressed as force times the change in time. And if you look at this graph that we have on the slide, you can see the force times time. And a lot of times these are the types of problems that come in because you can just find the area under the curve, which is just those red lines in the triangle. And it is sometimes, it seems like a really weird concept because change in momentum doesn't seem to be that helpful, but it allows us to connect variables like time and force to momentum, which is obviously super helpful because it deals with mass and velocity. And here are some really basic examples, and I'll give 3 seconds to pause and try both of these problems. So first up, a car starts out with a momentum of 30 kilograms times meters per second and ends up with a momentum of 45 kilograms times meters per second. What is the impulse? So this is really simple. Impulse is the change in momentum. So you just subtract these two quantities and you get 15 kilograms times meters per second. The second one, if a ball is hit with a baseball bat with 4,000 newtons of force, and for 3 times 10 to negative third seconds, what is the impulse? If you look at this, it's just applying the other formula. The impulse is force times the change in time. Therefore, you are pretty much just again multiplying these two quantities and you get 12 kilograms times meters per second. And the second type of problem is dealing with the graph that we showed earlier on the slide. So the question is, a constant force of 80 newtons acts on a 10 kg block for 5 seconds. What is the impulse exerted on the block during this period? And what is the impulse exerted if the force increases from 0 to 80 newtons at a constant rate? So again, around 3 seconds to pause the problem and give it a shot. So first up, what's really helpful is trying to draw this on a graph. Of course, this is just, again, the same problem as what was there before, where you multiply the two quantities. But it's a different way to interpret the problem, because if you see on the graph, we have that it is at 80 newtons for the entire 5 seconds of the time. And therefore, if you're trying to find the area in that square, just like earlier, you multiply 80 times 5 and get 400. And here are the newtons we have. The unit is Newton times second. It's really just the same units, but this is more preferable because we're dealing with force and time. And the second problem is especially helpful to draw the diagram because it isn't as intuitive as the other one, because the force is actually changing. So when we draw this graph, we can see that it is just a triangle. And therefore, we can use a simple geometric equation, that 1/2 base times height, and therefore 1/2 times 5 times 80. So it's actually 200 Newton seconds.
So for collisions in one dimension, we have two main types of collisions. We have elastic and inelastic collisions. In an elastic collision, we conserve kinetic energy. Note, this is different from conserving total energy because everything is going to conserve total energy. And then we have inelastic collisions, which cause two objects to stick. This does not conserve total kinetic energy. So as we can see in these two diagrams, before the collision, we see that the masses, they stay the same, but now they have different velocities as before and after. Whereas before, or for an inelastic collision, we have two masses, they when they collide, they have a new velocity and a new mass, the new mass being the combined total of the two masses of the two balls. Consider a ball of mass m with velocity v naught, and which collides with elastically with a ball of mass little m with velocity little v naught. Find the final velocities of both balls. Assume there's no friction. This one is tricky, so we'll give you 3 seconds to pause, but this is definitely the most optional chance to pause because it's a long problem. Okay, so for this problem, we start off with our formulas for kinetic and kinetic energy and momentum, since they're both conserved. We then do some simplifications. Annotate. Here we have this formula comes directly from our conservation of energy formula. And then we also have from our conservation of momentum that m times v, or big V naught minus big V equals little m times little v naught minus, or little v, little v minus little v naught. We can then just divide these and get this, or get these two equations. V naught plus v equals v naught plus v, or little v naught plus v little v, and this is the same as big V naught minus little v naught is equal to little v minus big V. We can then use a system of equations and solve them to get these following equations. And just doing some algebra, we get our final equations, which are rather complicated. By no means do you have to memorize these. Usually you're not going to be given a question with just 4 variables and then asked to solve it. You're almost always going to be able to just solve them algebraically with much easier numbers and far less variables. But this is the most general case. Well, let me just get rid of those annotations. This one, on the other hand, is far easier. A ball of mass 2 kilograms and velocity 2 meters per second collides and sticks to another ball of mass 10 kilograms and 0.5 meters per second. What is the final velocity of the system? I'll give you like 3 seconds to pause and figure it out. Okay, so since they're sticking together, we know that the collision is inelastic. So our formula is going to be M1 V naught plus, or actually V1 actually, because notation, and then M2 V2 is equal to M1 plus M2 times V. Then we can simply solve for final velocity. We're going to have, so we have M1 V1 plus M2 V2 over M1 plus M2. And that's equal to V. Then we just plug everything in and we have we have 2 times 3 plus 10 times 0.5 over 2 plus 10, which is equal to which is equal to 0.92 meters per second. And that's our final answer.
Thank you everyone for joining us today. It was really great. Make sure to like, subscribe, and comment on this video. And if you want any more content, feel free to join our Google Classroom with the information in the description below. Thank you.